Hi, everyone. Today I'm going to talk about lists. Like, suppose you want to store in a computer a list of items like your shopping list. The obvious way to do this is to use an array. So let me write down the obvious thing. To make it simple, I'll show you a little bit of code where we actually store a list of ints, but you could store a list of objects the same way, as an array. It's a simple, easy, obvious idea, but there are some disadvantages to it which we should know about so we can look at alternatives. So here are the disadvantages of array-based lists. First of all, suppose you want to insert an item at the beginning of a list or in the middle of a list. Well, if it's your shopping list, why would you want to do this? Maybe you don't care. You can just add items to the end. But there are a lot of kinds of lists that the computers work with especially, that need to be kept in a particular order. Like if you're the phone company and you're publishing a phone book every year, you can't just put the names and phone numbers in a random order. You have to have them in alphabetical order, or it's not a very useful book. So if you need to insert a new item, someone gets a new phone number, then you might have to go at the beginning of the list, and if that's so, that takes time proportional to the length of the array. And if you're not convinced that that's true, I'll show you why it's true in a minute. But first, let me list the other problem, which is that arrays have a fixed length. So in Java, you might allocate an array of length 1,000,000. After all, the world's never going to have more than 1,000,000 phone numbers, right? But then, the world surprises you. So let's just take a quick look at one method that would try to deal with both of these problems when you want to insert one new item into a list. So here it is. Here's my list class. What does my list class consist of? Well, there's a reference called A, which I can use to reference an array. Maybe we'll start off with room for 10 ints. And there's an int called last item, whose job is simply to be an index to the last item of the list. So if there's 8 items in the list, last item will be 7, because 7 is the index of the last item. They're indexed from 0 to 7. So that's what my list class is. And let's look at a method called insertItem that inserts a brand new int at some particular location in the list. How do we do that? Well, suppose I want to insert a new int 4 at location 2. Well, I've got all these other numbers in the way, so I have to walk through from the end of the list backwards, moving all of these numbers over to make room for the 4, assuming that the order of the stuff in the list actually matters. And that's the part that's going to take time proportional to the length of the list. So if there's 1,000,000 numbers in your phone book, that's going to take a long time. Then you finally free up room for the 4. And so that is what this method does, is here's the loop that walks through the list from the end to the middle, moving all the items over one at a time. And then finally you can put your new item in and increment the number of items. But the other trouble occurs when you fill up this list and you want to insert yet another item. And so what do you do then? Your array is full. There's no more room. You have to allocate a new one. And so we have this additional chunk of code here whose job is to allocate a new array, copy all of the items from the old array to the new array, and then you can go ahead and insert the new item as usual. So this seems like a lot of work. You know, your computer has to run through these things. It takes a long time. We want to do something else. The something else we're going to do is called linked lists. And for those of you who've learned Scheme, linked lists should be very intuitive to you. So linked lists are built into Scheme. They're just a natural part of the language. But in Java, they're not. So Java, you actually need to explicitly create them and define them yourselves. So we're going to define a linked list class. And this is going to be one example of a recursive data type. The reason the recursive means that the definition of the linked list class is actually going to refer to the linked list node itself. So here's what a linked list is. It's a list that's made up of data structures called nodes. And each node stores two things. It stores an item. If it's your shopping list, it can store the milk. And it stores a reference to the next node in the list. And if you've learned Scheme or Lisp, then these two things are just like car and cdr. They are completely analogous, except that they're not built into the language. You have to actually declare them by creating your own node class. So here we go. Public class list node. We'll have an item. For now, we'll just use ints, because that's simple. And a reference called next, which is pointing to the next node in the list. You'll notice that I'm using list node to declare a variable, to declare a field, before I even finish defining the list node class. And that's okay. That's part of why I said this is a recursive data type. But Java lets you do that. Not a problem. So now we've got a class. Let's go ahead and make some list nodes. Okay, there's a declaration that declares 3 new variables and assigns them all new list nodes. And since I'm calling the constructor 3 times, I get 3 different list nodes. Okay, I'm going to fill in some items. Like, let's say that L1.item is 7, and L2 dot item is 0, and L3 dot item is 6. So there we go. There's the numbers we want to store in our list. And then the interesting part comes when we link those list nodes together into a list. So I set L1.next equals L2. And recall that what this does is it takes whatever reference is in the L2 box and it stores it, that value, in L1.next, making a copy. So this reference gets copied into this box. And now they both point at the same thing. And likewise, L2.next equals L3. So that writes a reference into that box. And what about the last node? Well, I want my list to end with 6. I have no more items after 6. So I need a reference that doesn't reference anything. And in Java, that is called null. Null is the reference that doesn't reference anything. Yes? The default value for a list node? You mean what's the default value that gets written into a reference? Null, actually. So, in fact, you could leave this line out if you're writing Java, but I suggest you get in the habit of writing it in anyway, because someday you'll probably have to code in C, and then there will be random garbage written in this box, because that's what C does, and you will need to actually make sure to null it out. So I'm going to use an X in the box to represent a null pointer. Question? Does what have to be capital? In list node, does node have to be capital? If that's the way I declare it, then that's the way it has to be. Nothing. No. Oh, does null have to be capital? No. In C, null is in all caps, but in Java, null, it has to be lowercase. So there you go. In Java, lowercase null only. Any other questions about any of this so far? Yeah. So you're asking why this is pointing to this and not to this? Okay. Well, first of all, this is a variable in Java, a local variable, and there is no way to get anything to point at a local variable in Java. That's just not an option. You can only have references to objects, not to variables. So that isn't even possible. What a statement like this does is it takes whatever is in this box and it copies it into another box. And so you can't create a pointer directly here, but you can take this arrow, which points to a particular object, and make a copy, so now you have two things pointing at the same object. And that's about the only thing you can assign, the only way you can assign references. Any other questions? All right, so one thing that we don't have here that those of you who've programmed in Scheme might find convenient is a const operation, but we can create one by creating a constructor, or several constructors. So let's add some node operations that are basically versions of const, just to simplify programming and make our programs a little shorter. So I'm going to declare a list node constructor where I can just feed it the item and the next reference. and it'll go fill in those fields for me. And that just lets me use a shorter syntax to create new list nodes. So again, this is basically our way of implementing const operation in Java. And sometimes, if the next pointer is null, it's nice to have a shorthand version of that. So let's throw in a short constructor too. So hopefully you learned this notation in lab. I'm going to make this constructor call the other constructor, filling in null for the next reference. And so now I can create a list like that all in one shot by writing something like this. Ta-da! Of course, there is one difference between this code and the previous code, which is that this code does not set up the L2 and L3 variables. But if you just want to make a quick list, here you go. All right, now that we've got... Oh, question, yes, yes. Uh-huh.
And you try to assign something to like fit in the middle, do you just have two references to the same node, right?
Well, I mean, if you execute this, after you execute that, is that what you're saying?
No.
Okay. If you...
You've already got your list, and then you decide to call this node of 6, and
Uh-huh. Okay.
So would it error?
Well, I mean, I think I would have to know exactly what line of code you were writing to answer your question.
I guess I'm just thinking, how would you insert a new node into the middle of a list?
Oh, okay. I'll give an example of that in a minute.
Okay.
So hang on, and I'll hopefully satisfy your question. Any other questions, though, before I go on? Okay. So now that we have these node-based data structures, I want to talk about the advantages of them over the array-based list, including what this gentleman just asked about. So the first advantage is that if you want to insert an item into a list, into the middle of a list, say, then that does not take time proportional to the length of the list, like it did with arrays, as long as you have a pointer to the right spot. So instead, it takes a small, constant amount of time. Of course, admittedly, that's a big if, but there are certain cases under which it's really true. And the second advantage is that you don't have to worry about how long your list is or how big an array you created, because the list can keep growing until memory runs out. So if you have enough memory in your computer for 1 billion list nodes, you can store 1 billion items without ever having to resize an array or fuss with that. And I don't want you to think there will be only advantages for linked lists. There will be disadvantages too. But before we get to those, let me talk about how you do this inserting an item. So here's a method to insert an item immediately after this node. This method has to go inside the list node class, of course. I will call it insert after. And it just takes, as its input parameter, one item, which is the new integer you want to insert. There's my method. And suppose I want to insert a new item into the list. And I want to insert it here between L2 and L3, between the second and third items in the list. And I have the pointer to L2. So now, from some other method, I can just call L2.insertAfter three and insert a new node into the list. Now, we want to understand this piece of code here. It's one line, but it's a little bit of a tricky line, and here's why. If you mistake Java's assignment notation for mathematical equality, this line is very, very confusing because next appears over here, next appears over here. You might think that this is an equation you're solving for next or something. But you have to understand that these are two completely different values of next. Why is that? Well, this is an assignment statement. It computes a value and it assigns it to the variable next. But before you can do the assignment, you have to compute that value, which means you have to call the list node constructor. But before you can call the list node constructor, you have to evaluate the parameters and pass them in to the list node constructor. And so what that means is that this is the old value of next before the assignment executes. And this is going to be a new value of next after the assignment executes. And I can promise you that most of you are going to get mixed up on trying to write code like this at least once. So try to remember this fact, that first you read in the old value, then you do some operation, then you assign a new value, and don't get the old value and the new value mixed up. Yes? Uh-huh. Well, this node is not going to get lost, but let's go ahead and execute this and see what happens, and maybe that'll answer your question. So let's execute this line of code here, L2.insertAfter3. What does it do? First of all, it reads, well, item is set to 3. because we're calling insert after with a parameter of 3. And so now this line of code executes, and it executes roughly from right to left. So the first thing that happens is that these values get evaluated and passed to the constructor. Item is 3. Next is the old value of next. And since we're called insert after on L2, this next is really L2.next. L2.next is this reference here. So this reference here is the value that is getting passed in here as next. All right? So now we call a list node constructor, and the list node constructor creates a brand new list node whose item is 3 and whose next value is the reference that was passed in to the constructor. This reference here. So this value gets copied into this box. Then the constructor returns a value. The value it returns is a reference to this list node. And that value gets copied by this assignment statement into the next box. And again, since we called this on L2, that's L2.next. So we follow L2.next, and we copy this value into this box. So now you can see we still have a linked list. It flows in the direction we expect, 7, 0, 3, 6. Any questions about that? Yes? In that case, you don't have to say this dot next, but if you did, that would be fine. If you write this dot next, it does exactly the same thing. Question? When you create a new node, well, there's no variable that points to it. So if that's what you mean by a name, there's no variable anywhere. Well, actually, there is a variable. Inside this constructor, there is a variable called this that points at this node. And that's the variable that gets returned by the constructor. Right. So right now, we can't call insert after to insert something after this node because we don't have a variable to do it directly. But we could still do it indirectly. If I wanted to insert something after this node right now, one way I could do it is I could say L2.next.insert after. So what does this do? It looks up L2.next, which gives us this reference here, and then it calls insert after on this reference. And so now you can insert something after this node in that way. Question? Well, if you want to insert like a million nodes this way, this is not a very efficient way to do it. You need to think harder and come up with something better. But yeah, if you wanted to do the next one, you would do L2.next.next.insert after. And after that, you could do L2.next.next.next.insert after. It wears out after a while, of course. Yeah, you can make a new reference variable and have it point to this guy here and save yourself that trouble. Yes, you can. Usually, you're going to have algorithms later on as we work with lists that do specific things, and they'll be walking through the list, and they'll be at particular points in the list for particular reasons at particular times. And you'll see once you actually program a few. Did you have a question? Well, one way to do it would be to insert them in reverse order so that you don't have to do this .next.next.next. The question was, how would you insert 1,000,000 values into a list? So one way is to do it in reverse order, always inserting new item at the front of the list, but because you do it in reverse order, they come out forward. Like, because you're inserting at the front of the list, right? First you insert 4, then you insert 7, then you insert 6. So you're inserting them in reverse order of what you would expect. The second way you could do it, you could actually keep a little extra variable whose job is to always walk to the new item after you create the new item. So you can do a little loop that's like, for however long you want to repeat this, L2 dot insert after I, and then just say L2 equals L2 dot next, and ta-da, now L2 is created. Now L2 is pointing to the thing you just created, and now you can insert another list node after that and do it in forward order and do this as often as you want. So if you want to do them in forward order, this is the natural way to do it. Other questions? Yes? Well, now that's hard, and here's the reason why. Suppose I want to insert something before L2, say, before this node. Then I've got a problem. In order to insert a node here, I need to change this next pointer so that it points there. But starting from L2, there's no easy way to get to this node because I don't have a way to walk backwards in a list. So the best I can do is I can start from the very beginning of the list and walk forward until I find the node whose next pointer is equal to L2. So doing that is actually kind of hard, and that's one of the reasons next, on Friday's lecture, we'll discuss doubly linked lists, which makes that easy. Other questions? All right. So we've seen insertion into a list, and I gave you a list of advantages of linked lists over array lists. Let me say some disadvantages now. Suppose you don't have a pointer to the item in a linked list that you want to look at, but you know that it's the ith item. Like maybe you want to look at the 5 millionth item in your billion item list. Well, finding the nth item of a linked list takes time proportional to the length of the list. Let's just call it n. The number of items in the list is n. Also referred to as the length of the list. Now, the reason this is strange is because with arrays, you can do this in constant time. So here's a case where arrays have a big advantage over linked lists. So there's kind of this weird trade-off. With arrays, it's easy to find the 500 millionth item, but if you want to insert a new item after it, that takes a long time. With linked lists, finding the 500 millionth item takes a long time, but inserting an item after it is like just a snap. So we've got this tension between these two different ways of storing something, And a lot of the data structures that we will study this semester, like hash tables and balanced binary trees and so forth, are actually going to be ways of trying to find a compromise between these two data structures that works quickly in all of the different cases we want to do, both finding items and inserting new items. And so in a sense, this trade-off is kind of the theme of this course. So let's get a little more practice with lists. Let's write some code that finds the nth item in a linked list. So it's called nth, nth. And the idea is you pass in a position, and it finds the nth item in this list. And if position is 1, that means the very first item, the one that we're pointing at right now. So we're not numbering from 0, we're numbering from 1 here. So if position is 1, then we're already there. So just return this. We are already at the right list node. Otherwise, let's do some error checking here. So maybe the user called this method with position less than 1, in which case we cannot fulfill the promise. We can't give you the -3th item in a list. And the other thing that might go wrong is that maybe the user has asked for the 10th item in the list, but the item we're at right now is actually the last item. There's only one item in the list. So in that case, there is no 10th item. So if the next pointer is null, again, we have an error. We cannot deliver what we were asked for. And so in these two cases, where the thing we're looking for just doesn't exist, just return null. But if neither of those things are true, then we're going to use recursion. So the idea is, I'm going to go jump to the next item in the list, and I figure if I have a list like this, okay, what is the 4th item in this list? Here's the 4th item in this list. So what I'm going to do is I'm going to look at the list that starts at the next node. So if this is a list of 4 items, then I can jump to the next item, make it the new this, and now this list, the item I'm looking for is the 3rd item in that list. So my recursion is going to use that idea, that if I jump forward 1 node, in other words, if I jump to the next reference, then I can call nth recursively on that node, and the position is 1 less. So there we go, a recursive method for walking through a list. Any questions about this? Yes? Mm-hmm. Yep.
After that method has completed, won't that reference have changed?
Well, no. So the question is, if I call this method on a node that I have a reference to, when it returns, will that reference have changed? And so that's not how it works. Let's see how I call this method. Okay, so here's a list. And maybe some other method has a reference to the first node of the list called L. All right? So how am I going to call this? Well, there's several ways I could call this. But if I want the fourth item in this list, maybe I'll do it like this. I'll say list node L2 equals L.nth 4. So when this method completes, what will happen is L.nth will return a reference to that node. And the assignment statement will copy that reference into L2. But the original reference, L, that you called nth on, hasn't changed at all. It still points to the same node it always pointed to. So far I've been talking about lists of integers, ints, but it's handy to have lists that can reference any object. How do you do that? Well, in Java, if you want a reference that can reference any object at all, then you declare a reference of type object. And object is spelt with a capital O. So here's my slightly modified class. I'm going to modify the name slightly too, and I'm going to call it slistNode. And S stands for singly linked. The lists that we've been studying today are singly linked lists. Friday we'll study doubly linked lists as well. But I just want to get the convention started now of throwing that S in there for singly to distinguish these from doubly linked lists. And you will see these slist nodes in next week's lab and next week's homework. So now that we've got this slist node class, I also want to create a separate list class. Let me motivate why I want to do that. There are two problems with just using list nodes by themselves. So here's problem number one. Suppose that I have X and Y both being pointers to the same shopping list. So maybe X is me and Y is my roommate, and we're sharing this shopping list so that if one of us goes shopping, we'll get enough food for the whole house. Okay? Now, suppose I insert a new item at the beginning of the list because I just remembered that we're out of soap. How do I do it? Well, I could say something like X equals new slist node soap X. What does this line of code do? it creates a brand new list node that points to SOAP and has a next pointer which points to the old value of x. And then, once that list node is created, it does an assignment to x of this brand new list node that I've just created. All right, so now my shopping list has soap and milk. And then my roommate goes shopping and buys milk and forgets to buy the soap. Because my roommate's list wasn't updated, just mine was. That's not good. A second problem is this. How do you represent an empty list? Well, you might think it's obvious. A null pointer. You set x equal null, and ta-da, now I have an empty list. Here's what's wrong with that. If you have x set equal to null, you will get a runtime error if you ever try to call any list method on x. You get a runtime error when you try to call any method on a null object. Even though Java knows that x is of type list node. And there are good reasons for doing this, which you'll learn about later in the semester when we learn about dynamic method lookup. So for instance, if you try saying x.nth1, instead of getting the null pointer back that you would hope for, you'll just have your program crash. So the solution to these two problems is a separate slist class that maintains the head of the list and whose job is to maintain the head of the list in a separate data structure. So let's go take a look at that. So here's the slist class, and you'll notice two things about it. Every slist has a head, which is the first item in the slist, and it also, just for convenience, keeps track of the size of the list, which is the number of items in my shopping list. And so a typical list would look like this. Here's an slist object. It keeps track of its size. And it keeps track of its head, which is the first item in the list, which is an slist node, just like what we had before. So there we are. There's a list that has one item in it, namely milk. And now, instead of pointing to the slist node item, as we did before, now me and my roommate are going to both point to the slist. So if I add a new item to the shopping list, my roommate gets the new item in the shopping list as well. And there's no more of these conflicts. Of course, another advantage is that there's this size variable which keeps track of the size every time we do an operation on the list, so that if my phone book grows to 1 million entries, I can just look up how many entries are in the phone book instead of counting them all. And finally, if I want to represent an empty S list, I don't set X to null, I don't set Y to null. Instead, I just set head to null. So here, right here, this constructor is how you represent an empty S list. You just set the head to null. And then if you want to call methods on S list, they won't crash just because the list is empty. And so, any questions on that? Yes? I can't hear you anymore. Uh-huh. Does it write an object? Oh, that means it could be any object in Java at all. That's what it means. Yes, sir? Well, we have to rewrite all of our methods that operate on lists so that they always remember to update the size field as well. We're not going to call methods on S-list nodes anymore. We're only going to call methods on S-lists. Actually, you'll see examples in the lab and homework next week, so hopefully that'll make it clear